part of our nervous system, which is our muscles. So last time we talked about generation of action potentials, and then we talked about synapses and how synapses can lead to memory and learning. And so one of the things that synapses do is they the motor part of our body that allows us to talk and move and so on with the nervous system. And so basically these are some of the learning objectives that we have for today. So there are at least three different kinds of muscle tissue. What we're going to talk about primarily today is the somatic, or what we call the voluntary striated muscle, which is under the voluntary control of our brain. And we also have smooth muscle in our eyes and our gut and the uterus. We're going to spend a little time talking about the uterus and its role in labor and delivery. We're not going to talk at all today about cardiac muscle because that's actually the topic for the third module of this class. And so Amy's going to give you, I'm sure, a good insight into cardiac muscle. So these are different kinds of muscle. They're innervated differently. They do different things. And one of the things that kind of is characteristic about the striated muscle is it looks striated. If you actually look at it under a polarization microscope, you can actually see it move. You can actually study it because it's very highly ordered, and because it's very highly ordered, it is very highly birefringent. And so it makes it actually kind of easy to understand and study it. And so there are a couple of kind of terminologies that kind of important. So individual muscle cell is sometimes called a muscle fiber. The reason it's called fiber is because the muscle cell is very long. It can be up to 1 meter long. So this is one cell, one single cell that's 1 meter long, goes tendon to tendon. The cell membrane is sometimes called the sarcolemma, and the cytoplasm inside the muscle cell is called the sarcoplasm. One of the things that's characteristic of striated voluntary muscle, it has a very well organized sarcoplasmic reticulum, which is very important in the transmission pathway for the control of its function. And so the sarcoplasmic reticulum you can think of as a big reservoir that stores calcium inside the cell. And so again, kind of in terms of the way that we divide the anatomy. And so we have a muscle, that's the big macroscopic thing that you can look at, muscle, and then inside that muscle are fascicles or groups of cells. And then finally, you kind of get down to the single muscle cell with muscle fiber, which is kind of a multinucleated but still very, very long cell. So this is a really good diagram. It kind of shows kind of the important things that are the main actors in the muscle contraction. And so basically we have the cell membrane, the nuclei are on the outside of the cell, towards the periphery. Muscle cells have a lot of nuclei. They're not just one. They're scattered around the outside on the sarcolemma. And then there are these little tubes that go down, kind of invaginations of the cell membrane that go down and surround the contractile components. These are called the transverse tubules. And they go down kind of close to the sarcoplasmic reticulum. And then you have this kind of bluish kind of area here, which is where calcium gets sequestered on the kind of the outside of the individual muscle cell itself. So again, it's kind of so the muscle fiber has these myofibrils. This is kind of the lowest division that we're going to go into, which is the contractile component for the cell. So this is another good diagram that's out of your textbook. It kind of shows the relationship between these transverse tubules, the sarcoplasmic reticulum, and the contractile component, which are a couple of very important proteins called actin and myosin. So if you look at the individual contractile component, myofibrillar, you actually see that you kind of see some different bands, which is why it's kind of a stripe. And these correspond to the various structures and the overlapping of the actin and myosin inside the myofibrillar. We know if we further kind of subdivide it that the production of force is actually by the sliding of the actin past the myosin heads. And we'll look at that in more detail in just a minute. Anyway, you can see these things with the light microscope and study them. So the big protein here, the big actor here is myosin. Myosin is a fairly large protein. It has a kind of a head to it that binds into the actin. The actin is relatively thin, but it has binding sites for the myosin. And the way that the contraction is controlled is because there's another protein called tropomyosin, which blocks, ordinarily it blocks the head of the actin, or the binding side of the actin from the head on the myosin, so that they can't bind. And so if they can't bind, they can't produce force. Ultimately, the control over the contraction summary here is this other molecule, which is called troponin. Troponin is a binding site for calcium. And when the troponin binds calcium, the tropomyosin rolls, it changes its configuration and moves away from the binding sites in the actin become exposed to the myosin from binding into it. And so, of course, this is a three-dimensional structure. If you look at kind of the place where all of the proteins are kind of overlap, you kind of see a picture like this where you have the myosin and the actin in this kind of three-dimensional structure. If you look where there's just myosin or just actin, of course, you just see that particular part of the contractile component. The whole structure is kind of held into place by another kind of a structural protein called titin, which kind of supports, keeps everything aligned, and kind of keeps structure during the actual contraction. And so again, as I said, you can see in this diagram, actually a light microscope picture of the contraction of a single contractile component here, where you kind of see it in the kind of resting state when it contracts. And as you can see, what happens is the A line here, which is kind of the A band, which is kind of the overlap, is going to get closer and closer over here to this Z line. And so the Z lines become compressed, which is how you get force, you change length. Now there are different kinds of muscles. If we look at the different kinds of striated muscle, we have some that are very fast. A good example of that is the knee. Question.
So I was going to ask this a while ago, but the troponin, is that located in the tissue wheels or on the actin fibers?
Actin.
Oh,
It's close to it.
Okay.
So if you look at the actin fiber, it's kind of shrouded by the tropomyosin, and then the troponin is the binding site for the calcium. When the calcium binds, the tropomyosin rotates off of the binding sites on the actin.
Okay, so the myosin can then get on.
Can then bind to the binding sites.
That makes sense.
Right. So anyway, we have different kinds of muscles that do different kinds of things. For example, in your eye, you have 6 muscles that move your eyes. One of them is called the medial rectus muscle. You'll learn a lot more about that during the next part of this class. But these muscles in the eye are very, very pale. When we're operating on the eye, the muscle looks almost transparent. So, it's completely different than what you would see with a muscle, for example, in your eyelid or in your leg. And so these are pale as opposed to the bigger muscles, for example, the soleus muscle. And the reason is because the fast muscles really don't have myoglobin, which is really helpful for transporting oxygen into the muscles that produce most of the force. And so really the fast muscles are fairly poorly vascularized with few mitochondria. The big muscles in your leg have lots of mitochondria. The ones that are the anti-gravity muscles undergo a lot of oxidative metabolism, Krebs cycle. And in the eye, primarily glycolysis. One thing that's very interesting is that the eye muscles in the eye, for example, the pale muscles, they can contract with very, very high intensity for a short duration. And that allows your eye to make saccades. And so basically it allows you to create a lot of angular acceleration, 20,000 degrees per second squared, huge accelerations. But they're very easily fatigued. They fatigue quickly, as opposed to the muscles in your leg, which are fatigue resistant, they contract much slower. And so they do different things. And so they look differently and they do different things. So here, the W is kind of a tail, fast twitch muscle, perhaps from the eye, and then this would be a bigger muscle, maybe from your leg. And you can obviously see the difference just in the photograph. Normal muscle, again, the fibers have the nuclei towards the outside of the cell. Here's an example of a patient that has Duchenne's muscular dystrophy. You can see that there are several characteristics. First off, the cells split. The nuclei move into the center of the cell. And these are pathognomonic. These are telltale signs that this person from whom this was biopsied has some very serious problems with the striated muscle. Have you all ever known somebody who had muscular dystrophy? Yeah.
Yeah.
Do what?
I know someone who's muscular dystrophy.
Yeah. And what? Can you tell us about the case?
I'm not really sure about the specifics because he's just like a acquaintance, but he's just has some problems with movement. He can't like run very much or undergo a lot of physical activity.
How old?
He's my age.
About your age? That's unusual to have lived that long. Yeah.
I had a question about the fast muscles. I was wondering where else they would be located besides just the neuron.
The fast muscles, we have the fast muscle in your ear, the tensor tympani muscle, primarily for how we look for the fast muscle. So Duchenne's muscular dystrophy is a fairly common problem. It actually affects 1 in 3,000 males. So you can see it's a significant problem. And it's X-linked recessive, which means being X-linked, that females can be carriers, but they don't manifest the disease. And we know that it's a mutation in a very specific gene which codes for some protein or structural proteins inside the muscle cell. Typically, it starts at about 5 years of age. The person is absolutely normal up until about the time you go to kindergarten and start school. And it usually starts kind of with more of the central muscles, the girdle muscles, that basically a child might have a little more trouble getting up out of a chair, or the anti-gravity muscles kind of get affected first. It's a progressive, relentless disease, and most people die by the time they get to be 20 years of age, which is why that case is a little bit unusual, because most folks don't make it that far. There is no specific treatment, but obviously this is something that biomedical engineers might be able to help with some kind of perhaps gene therapy or some other way to intervene with this really very sad problem. So we all know that we can control the strength of our muscle contraction. We can pick something up very gently, or we can lift something very heavy. And the way that we do this is by recruiting things that are called motor units. And so it's important to understand that in your spinal cord and in your brainstem, you have a pool of neurons, which are called alpha motor neurons. And these are very special cells. They're also called lower motor neurons, as opposed to upper motor neurons, which we'll study a little later. But these cells, one cell in your spinal cord, in the anterior horn of your spinal cord, will innervate a group of muscle cells. So we have one cell, one neuron, which goes to maybe 20 or 30 myocytes, muscle cells, not muscles, but muscle cells. so it turns out that this is the smallest addressable unit of force that your brain can bring in. In other words, if you wanted to know the absolute smallest force, you would recruit just one motor unit. As you want more and more force, what you do is to bring in more and more motor units, which innervate more and more muscle cells, and that creates more and more and more force. Okay? And so it's a very important concept. One neuron in your brainstem, your spinal cord, goes to a group of muscle cells, and that's called the motor unit.
Question. So does the motor unit include all of the muscle cells that it innervates?
Yes.
Okay.
It's the neuron and the muscle cells that it innervates. There's not cross-innervation, so you don't have overlap. In other words, they're exclusive. That neuron goes and innervates that group of muscle cells. And another neuron is going to innervate another group, independent group of muscle cells. Okay. Any other questions, Eric? Yes.
Two neurons innervate muscle cells in the same muscle?
Yes, absolutely. They oftentimes do. And so you see, as you bring in more neurons, you make more and more force in that muscle. Right? So some motor units are large. For example, in your leg, some of the motor units, the soleus muscle might have one neuron and 200 muscle cells. Okay, as opposed to the eye, where you have one neuron that only one neuron goes to only 3 cells, 3 muscle cells. Okay, so those are large motor unit, small motor unit. Okay? Now guess which one has the most control over the force that you can produce?
Small.
Okay? The smaller one has the most control or can grade the force much more precisely. Now that's kind of important. If you're looking around, you want to be able to point your eyes at precisely the same location. With both eyes, and you want to be able to track things. And so having extremely good control over the amount of force that you can produce is extremely important for the eye, and it's probably not so important for the leg. I mean, you kind of stand up and, it doesn't make any difference whether you have, 200, 400. You basically just want to get anti-gravity so you don't fall over, right? So it makes sense that you get better control over the muscle function with a higher density. It's called high density innervation. So the medial rectus has a much higher innervation density than the soleus muscle because it's got more neurons going to it. The nerve is bigger. Question?
Is there any difference in, say, reaction time or time it takes for these motor units to fire?
Yes. I mean, so the amount of time that it takes for the signal to get from your spinal cord to the muscle depends upon how far it is, okay, how long it has to go, okay, and depends on the size of the neuron. We already talked about that. And so if you look at the 3rd cranial nerve, 4th cranial nerve, 5th and 6th cranial nerve, they're big old nerves, big myelinated nerves. We're going to conduct quickly. Plus, the cell bodies are located really pretty close to the eye. You look at the 3rd cranial nerve, which goes to most of the eye muscles. It's in the part of your brainstem between the pons and the mesencephalon. Very close, not that far from your eye. Now, the nerve that goes to my leg muscle, that cell body is in my spinal cord. And if I look down to my lower extremity, that could be half a meter or more, right? And so if you just look at the same size diameter neuron, okay, it's going to take longer for that signal to go from my spinal cord to the muscle in my leg than it's going to take to go from my brainstem to my eye, right? Say all things else being equal.
there's no inherent difference between if it's a small motor neuron or a small motor unit or a large motor unit.
No, it has to do with the amount, smallest quantity of force that you can produce, not how fast you can produce. How fast you can produce depends upon how far it is from the cell body, right? You got the neuron here getting the signal, and the eye is only this far away, and your leg is this far away. So which one's going to get there first, my eye or my leg? Okay, it's going to be quicker to the eye. Any other questions? Okay, so we talked about this, already showed you this slide. Acetylcholine is the neurotransmitter at the myoneural junction. And unlike most other synapses, this synapse has 100% complete control. So when I generate an action potential in the alpha motor neuron, I will release so much neurotransmitter on the muscle cell receptor that I will always get an action potential in the muscle. Neuron, acetylcholine, action potential in the muscle. Okay? And this is blocked by what drug? What drugs? Is this nicotinic or muscarinic? No, it's nicotinic. And it's blocked by succinylcholine and chloride, even though the names of these drugs. So,
Can you repeat this?
so this is a nicotinic acetylcholine receptor. Talked about that last class. And it's blocked by drugs. A false transmitter would be succinylcholine, and another drug is called chloride. So basically, it's a nicotinic receptor block. Succinylcholine and chloride. It's in the last lecture. Look at your notes. Anyway, here's the contraction summary. This is what you have to memorize for this class. So there's action potential in the neuron, comes down the alpha motor neuron. Acetylcholine is released at the end plate. Acetylcholine binds to the receptors in the sarcolemma. Myocyte membrane depolarizes, i.e. creates an action potential in the muscle cell. That action potential travels down the transverse tubules into the sarcoplasmic reticulum, and the sarcoplasmic reticulum releases calcium intracellularly. So you get, all of a sudden concentration of intracellular calcium, which is a kind of typical intracellular messenger here. All of a sudden, it concentration goes way up, so your probability of getting a binding event to troponin goes way up. And so the calcium binds troponin. Once that happens, the tropomyosin changes its configuration, changes its three-dimensional structure, allows the binding sites on actin to be exposed. Myosin binds into the active site on the actin, and then you get what's called a power stroke. The myosin head rotates, and when it rotates, it's like a ratchet. It just pulls the actin right past it. So it goes plunk, 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 plunk. It shortens the muscle. Yeah, shortens the myocyte, excuse me.
When calcium binds protein, what exactly happens in myosin?
What exactly happens?
Yeah.
I mean, in terms of the exact stereochemistry, I have no clue. But troponin, is the controlling molecule which is associated with the tropomyosin. And that binding event of calcium in the troponin causes the tropomyosin to rotate away from the binding sites on the actin. So here's another out of your textbook. This is out of your text here. Kind of shows how the action potential is coming from number one. The action potential hits the alpha motor neuron down to the end plate. You release the acetylcholine. Acetylcholine binds into the nicotinic receptor, generates an action potential in the cell membrane, and this action potential then goes down these transverse tubules, and you release intracellular calcium. So calcium comes out. Calcium binds to the troponin, which then allows the tropomyosin to move away, so the actin heads are exposed and the myosin can bind, and thereby allowing the power stroke to occur. So here's another picture here. So again, regulated by troponin, and the troponin binds here, binds the calcium. The myosin head can now bind into that actin molecule. Without the calcium, the tropomyosin is blocking the binding site on the actin. So those two cannot bind, and you cannot get the power stroke. A little more detailed biochemistry, again, out of your textbook, kind of shows how the myosin head in the rigor state is, with no ATP binding, is very rigidly bound actually to the actin. Now this fortunately doesn't occur much while we're alive, but when you die, what happens to your ATP store? It's depleted very quickly, just within hours, minutes, and hours. And what happens when you die? You get stiff or you get limp? You get very stiff, and that's why you get stiff. This is called the rigor state. So anyway, if you have ATP binds very readily into the myosin head. It gets hydrolyzed into ADP and inorganic phosphate. And when it does that, it allows the myosin head to actually change configuration. And so when you have the ADP inorganic phosphate, you get a 90-degree binding between the myosin head and the actin. And then when you release the inorganic phosphate, the myosin head rotates 45 degrees, pulling the actin past it. So it's kind of tricky. What actually produces the power stroke is not the hydrolysis of the ATP, it's the release of the inorganic phosphate. Trick question. Okay? So then eventually the ADP gets released, you go back into the rigor state, and you're ready to go to another cycle. That's how the kind of the biochemistry of how the actual muscle on a very small scale, how that muscle ratcheting actually occurs. Okay, and so this is one of my favorite diagrams. It kind of summarizes that whole contraction summary in one picture. So if you understand this picture, remarkably, I think you'll understand most everything you need to know about the lecture for today. And so what I have here on these different scales, I have the measured the action potential. So this is something you can measure in the lab. Here's the action potential in the muscle cell. Okay, the second diagram here is the free intracellular calcium concentration. Okay, this is called the active state. I'll explain what that means in just a minute. And then I have a transducer that's in series with the muscle, and I actually measure the force that's produced by that single action potential. You can actually do this. This is an experiment you can perform. Just take a cat, cut the Achilles tendon, and then put a transducer on it, and you can actually get this data. So, real data. Now we're going to understand why this is important. Okay, so let's look at the time scales here. I didn't write, there's no time axis here, but the time scale here, you know for the action potential, what is the duration of the action potential? A few tenths of milliseconds, so maybe 0.2 milliseconds, 0.3 milliseconds, okay? And so if you look here, when this action potential gets to about minus 50, okay, it's going to go all the way up to the sodium equilibrium potential. But when it gets to about minus 50, and you have a free intracellular calcium concentration of 10 to the minus 6 molar. Well, that saturates. When you get to 10 to the minus 6 intracellular calcium concentration, that actually saturates the calcium receptors for the troponin. And so whenever this is over 10 to the minus 6, from here to here, you're in what's called the 100% active state. In other words, you have a power stroke which is occurring from this point to this point. Okay, that's when you have 100% saturation, 100% ability for the myosin to interact with the actin. Okay? Any questions about this action potential, intracellular calcium that we measure? And then this is just a depiction of that active state, whenever it was greater than 10 to the minus 6 molar. Now let's look here at this last diagram here. Now, this is what I measure with the transducer, which is in series with the tendon. Okay? have a transducer that's now measuring how much force that I'm creating. Okay? And somebody want to explain to me why it looks the way it does? Why do you see the force way after the action potential is done?
Is that when the actual myosin head moves?
You what?
The myosin head doesn't move till after it's finished?
No. Actually, when you're in the active state, we know that there's actually this oscillation is occurring from this point in time here to this point in time here. So you're actually getting something that's changing the length. So the length change is occurring from here to here. So you really don't see any force that's produced to right here. Yeah.
Is there a lot of slack in the slack?
Okay. So you're absolutely right. So how do we kind of model this? Okay. So let's suppose it kind of looks like, I would propose to you, kind of looks like I have a loose rope, right? That's the slack. And so I start contract, but I'm not going to get any force until I take all the slack out of the rope, right? Okay? So basically there's all of this slack in the system that I have to pull out before I can see the force. Now why does the twitch tension look like it does? Why does it look like this? What does that look like? If you're going to, in terms of mechanical terms, how do you model that?
Spring.
It's a spring, exactly. You're exactly right. So so here's my rope, which is right here. So I got this loose rope flowing around here like this. And then it's like the rope is attached to a spring here. And so I don't see any force until actually I get that rope is all the way stretched out. And then I start seeing what happens on the spring. And for spring, the force is equal to minus kx. So as I change x, my force will rise. Okay? So this part right here is this right here. I'm changing x continuously, okay? But I see a linear rise, almost linear rise in force until the contraction stops and it relaxes. And then I relax the spring. Okay? So that kind of helps to understand a little bit about the real world of the way the muscle acts. So we have this contractile component. This is what changes the delta x. Okay? But as delta x changes, I don't see anything until I get the slack out of the system. And then I see a gradual increase in force because of this series elastic component, which I model as a spring. Now, it gets even more complicated because there's a lot of connective tissue in parallel with the muscle. And so as it contracts, I'm actually compressing a lot of connective tissue, which we model as this dash box here, which produces heat. That produces heat. And then this stores energy, another spring, which is kind of parallel, which snaps back and then gives back the energy that is stored. And this is important because it turns out that our muscles are very, very important for the way that we regulate our body temperature. Okay? And so when we do work, the muscle contracts, and we actually have something that moves through a distance. We talked about that to actually accomplish something. And in that case, we use the muscle contraction to change the potential energy actually of that 20 kilogram block. I can also contract my muscle. I can push on this desk, and I can push and push and push, but I don't move the desk. Okay? And so that's called an isotonic contraction. When I do that, I'm using a bunch of energy. Okay? And that energy has to go somewhere, and it's going into heat. Yeah.
So on the slide it says it's isometric.
Isometric, and, yeah, did I say something
You
wrong?
said isotonic.
I'm sorry, isometric contraction. Isometric contraction. Okay. And so we use that, if you have an illness, and your body temperature is going up, you have chills. Ever had that experience where you just start shaking, right? That's the way your body produces heat to raise your body temperature when you have the flu, for example. Okay? So it's actually a very important part. We'll actually study temperature regulation in the next section, but that's important. This is the end product of what has to happen here. It also happens that there's kind of a magic link. If you don't have the actin and myosin overlap a little bit, you can't produce any force. And if it's all crammed up together, you can't produce any force either. And so there's kind of an optimal kind of in between where you get maybe a third to half of them overlap, where you can actually produce the most force. And most of our resting muscle length, is about that kind of length to give us the maximum force of contraction. Muscles consume a huge amount of energy, and so we constantly have to have this supply of ATP to power the power stroke. And so we have these stores of energy in this phosphocreatine, which allow us to generate large amounts of ATP. They're stored like a battery. And then eventually, if we get to where we've basically used up all of our stores, your body actually will convert over into the non-oxidative metabolism. So basically you go into the lactic acid cycle, so you start producing lactate. And then this will cause you to fatigue very quickly once you get to that point, once you've used up those ATP stores. This is what happens when you get to the 4.9 mile and 5 mile marathon. So very, very important concept here that we have two mechanisms actually for grading muscle force. We have the recruitment of motor units. We talked about that just a minute ago, where we can bring in more neurons firing, okay? More motor units, more force. But on a single motor unit, we can change the actual firing rate. So we actually have these two mechanisms that our brain uses. So I can ping the muscle fiber just a little bit on one motor unit and produce one quantity of force, but I can ping it a whole bunch, pop, 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 and I can produce much more force. This is called a tetanus. So if I have just a single action potential and it relaxes, so the spring contracts, relaxes, and then contracts, relaxes, contracts, and I don't have anything to add. But when I start pinging it much, much quicker, when I hit it within the decay constant for my spring here, I begin to get more and more force. And so I can go from no force to a sizable amount of force. This is called a tetanus. So we ping until we get the maximum force on that single motor unit. And eventually, of course, your muscle will fatigue, and then it goes back down to zero. So we have two mechanisms that control our grade, our brain uses to grade the force of contraction. One is firing rate on individual motor units, and the other is recruitment of motor units. Yes?
So is this similar to how in a neuron the action potential can be?
Yeah, it's very similar.
If it's pinged
Yeah,
in a
absolutely.
certain time range.
Yeah, what's happening is you're hitting it so fast that the calcium is not sequestered again. So if you go back to that diagram that I told you, the one I really, really like here, what happens is you're just extending that active state all the way out here. So your calcium is not being re-sequestered. So this stays, basically you're staying in the active state. Okay. And and we use this when we do artificial neural stimulation. We use both mechanisms. So we try to mimic the way the body works when we create prosthesis. So this is actually the way we design prosthetic control. So we also know from study that there are kind of different frequencies that produce the maximum contraction. And so for the muscle of the leg, the soleus, you won't get any more force if you go to 20. 10 pulses per second, you max out. Okay. The gastroc is about 40 per second. But believe it or not, the medial rectus muscle in your eye, it will grade its force up to 250 pulses per second. So again, you can see the eye muscle is getting incredibly more control, basically because it's got higher innervation density and because it has a much wider dynamic range of what we call the non-fused tetanus. Okay, both mechanisms. Again, kind of shows how you have these different motor units that go to the different muscles. And that's how we control our voluntary force of contraction. Any questions? Okay, so I'm going to change gears here, and we're going to talk now a little bit about smooth muscle. So we have a smooth muscle in our gut, we have smooth muscle in our eye, the dilated muscle of the eye. So there are two different kinds basically of smooth muscle. One's called the single unit, and the other is called the multi-unit muscle. The single unit smooth muscle is what you see in the small intestine, and it has really very, very little neural control. So you have here an autonomic neuron, which is releasing a neurotransmitter. There are various kinds, but this might be acetylcholine. It's binding into the muscle here, and that then changes the resting membrane potential, which allows the muscle firing rate actually to go up. And so if you look at this kind of muscle, if you actually make a recording, if I put an electrode into this type of smooth muscle, it has pacemaker activity. The muscle will spontaneously depolarize. And so you don't actually have to stimulate it with a neural impulse to have muscle tone. All that you do when you put the neurotransmitter on this kind of muscle is you increase its firing rate. And when you increase its firing rate, you'll increase the amount of force that you actually get with this particular type of smooth muscle. And so it's also true that the action potential here isn't being generated by a neuron to a muscle cell, but actually you kind of regulate the syncytium, you kind of regulate the autonomic activity of this muscle, which is contracting all by itself, and it's contracting, and the wave of contraction passes from one cell to the other because of tight junctions in the muscle cells. And so if you eat a big meal and you stretch the gut, okay, you stretch it, it'll actually contract all by itself. You don't have to have your brain doesn't have to do anything. It'll automatically contract. It reacts to stretch with no neural control. Neural control can regulate its excitability, okay, but it's not a direct neural control. Yeah.
Does that mean like things like your digest or your intestines basically are always somewhat moving?
Yeah, they're always moving.
Okay. And then at times it goes faster or slower.
Yeah, kind of sometimes, you know, you hear your gut's going sometimes, and sometimes you're real quiet, right? So it just depends on really how much it's distended. It'll react to distension. Now the multi-unit is different. It has direct neural control. And so here we have a neuron in the eye. This would be a branch of the third autonomic branch of the third cranial nerve, which is going to these individual cells, causing them to contract. So neural control, no neural control. Difference between these two. They're somewhat similar in that the smooth muscle does not have a well-defined sarcoplasmic reticulum. the calcium is sequestered in these little vesicles on the cell membrane. Okay? So if you look at it, these cells, they don't have the mechanism where you just get this huge release of calcium and you get the forceful contraction. All you can do here is just kind of regulate the autonomic activity in the smooth muscle cell. They still have actin and myosin, and the actual power stroke is quite similar. But the actin and myosin is really kind of more on the outside of the cell and causes the cell to actually kind of become more globular when it contracts. But it still shortens. Power stroke is still the same. Okay, but the neural control is different. Now there's one other kind of smooth muscle which is really important. I think it's good to introduce to it in this class. And that is what happens in labor and delivery. So I'm going to give you a little brief lecture on obstetrics here. So what's important for labor and delivery are the 3 P's. You have to remember these: the pump, the passenger, and the passage. That's all you need to know. Be an OB doc. Y'all remember that? The 3 P's. What's the 3 P's? The pump, the passenger, and the passage. Okay? The pump is the uterus. It's smooth muscle. Okay? Smooth muscle. Passenger is the baby, and the passage is the pelvic outlet. Okay? And so, labor and delivery is actually a terrifying experience for the baby. We probably don't none of us remember. It's not a particularly fun thing for the mom, but for the baby, it's terrifying. It has to all happen just right in order for the baby to come out good. Okay? And so, obstetrics is really, most of the time, doing nothing, punctuated by a few moments of sheer terror. Good description of obstetrics. And so, let's talk about the passenger and the passage first, okay? And so, what basically has to happen, the biggest part of the baby is what? The head. And the head has to fit through the pelvic outlet. Okay? If it doesn't, the uterus can contract all it wants, and the baby's not going to get pushed out, right? Okay. So, guess what? Us biomedical engineers have contributed immensely into maternal health by allowing us to actually measure the size of the baby's head and the size of the pelvic outlet. And so, with good obstetric care, which typically, if you look at how your obstetric visits are going to go, you get checked, every 2 or 3 months, during the first couple of trimesters. But in the third trimester, and particularly as you get to the last month, after past 36 weeks, you're going to probably have an exam every week. You're going to probably get an ultrasound. You're going to measure the size of the baby's head and see if it will pass through the pelvic outlet. Now, if you notice that the baby's head is too big, okay, you're going to let that woman go into spontaneous labor. No. Probably not. What are you going to do? You're probably going to schedule a planned cesarean section, because you know that labor is going to be unproductive, right? So, unfortunately, there are many women who never get prenatal exams. Did you know that? Even here in the United States. If you look at the World Health Organization has some really bad statistics that kind of show 2 out of every 100 pregnancies end up in really bad complications. And a lot of times it's because of not knowing in advance that there is a problem with the passenger and the passage. Now there's some diseases actually we know that create too big babies. One probably all ought to know that creates a big baby is what? So diabetes, is notorious for producing big babies. So you end up with a 11-pound, 12-pound baby, and if you get the baby's head too big, it's not going to pass. And so you've got to do a planned C-section. Okay. So this diagram is important for you to understand. Kind of shows the so the uterine muscle is not directly innervated. You don't have a nerve in your brain that goes to the uterus, so it's under the control of various hormones. And so the big players here, actually there's 3 big players: estrogen, progesterone, and another hormone called oxytocin. And so if you look at about the 32nd, 34th week, your progesterone level begins to drop, and the estrogen level goes up. Now what that does is it actually moves the resting membrane potential. It actually moves this resting membrane potential more positive. And as that membrane potential goes more positive, the uterus begins to contract more frequently. Okay? And so what we call this, kind of in this 34 to 36 week period, is what's called the Braxton-Hicks contractions. And this is also known as false labor. This is where the lady gets her husband and, honey, we need to go to the hospital. I think I'm having a baby. And we go to the hospital and the doctor checks her and she says, no, you're not in labor, go home. You'll come back, when you're in real labor. Okay. Y'all heard of that? Yeah? Okay. So the uterus is becoming more active. It's becoming, the membrane potential in those smooth muscle cells is going more positive, and it's spontaneously beginning to contract. Okay? That's important because it's now going to orient the baby so that the head is now engaged in the pelvic cavity. And one other thing that happens here is that in normal labor and delivery, with the head down, you're going to have 2 things happen. We're going to look here in a second. The cervix is going to dilate in place, and the other thing that's going to happen is the baby's head can get molded. Okay? Right? You ever seen a little baby that comes out, it's got a little pointed head? Right? Okay. Yeah, you've seen that, right? Yeah, so the baby's head, the bones aren't fused, so you can actually get molding, so that actually helps the baby to pass through the birth canal. And that's important because if this happens over, several week period, it's all hunky-dory, so we're good. But, if indeed, things get stuck, then we got potential disaster. And so there are a couple other things. So we got the Braxton-Hicks, and you're kind of beginning to contract, and you kind of feel like things are getting close. But let me mention one other thing. On this diagram, it's very important to also understand that if you have a lady, for example, that's given premature delivery or had trouble with kind of prematurely aborting, multiple pregnancy, twins, triplets, you've got to be careful because the uterus is going to become more, it's actually going to become more excitable early. And so a lot of times the OB doctor will actually start that woman on a progesterone patch. Okay, very commonly used is to prevent premature labor. Okay, and so the lady can take it with a patch. They also make rectal suppositories, and they make a depot that you can give too. So there's multiple ways you can actually give the progesterone. But the idea here is if you want to prevent the excitability, you want to increase the progesterone level so you don't go into premature labor. Yes?
Did you say that oxytocin?
Yeah, we're going to get to that in a second. So here's what's going to happen. So when you get down to the last week or so, What happens is the cervix, which is ordinarily fairly firm, is going to begin to get very soft. And so it begins to efface. And so if you palpate the cervix with your finger, you're going to find that the cervix is actually getting more mushy, and it doesn't have that kind of ridged contour that the ordinary cervix has. And that's called effacement. So effacement is going to start happening about 2 weeks before delivery. Okay? Now, once the cervix is fully effaced, then you